Hi, I'm Mr. Miller, and this is an introduction to trigonometric equations. So here's the first example. We're looking at solving 2 cos theta plus 1 equals 0, for theta being the angle between 0 and 2 pi radians. Then we want to find the general solution for this equation. So let's get started. We start with this equation, and we want to isolate the cosine theta. So we subtract 1 from both sides. We divide both sides by 2. We're looking for where is cosine theta equal to negative 1/2. And cosine is negative in these two quadrants, 2 and 3. So we draw terminal arms in each of those quadrants, and we make the side lengths fit the situation. So we know since cosine theta is supposed to be negative 1 over 2, that means this is your x over r. So negative 1 over 2 is the x over r. Of course, it could be drawn in quadrant 2 or in quadrant 4. Now, if you want, you can find the third side length just by doing 2 squared minus 1 squared and take the square root. So that's root 3. And of course, in the other quadrant, y would be negative root 3. And a 1, 2, root 3 triangle should look familiar to you. So we're looking for this angle, but of course, you must be thinking this angle is easier to find for starters. And this angle would be 60 degrees, right? 30, 60, 90 triangle, which makes this 120 degrees. And 120 degrees in radians would be 2 pi over 3. So that's the first solution, is 2 pi over 3. Now there is another solution on 0 to 2 pi, which is this one here. I'll label it theta 2. And you'll notice that that's equal to 2 pi minus theta 1. Because of the symmetry here, you notice that theta 1, this 120 degrees is here. This is also 120, well, it's negative 120 degrees here. So if you did 360 minus 120, that would give you 240 for theta 2. But of course, we're working in radians, so we're talking about 2 pi minus 2 pi over 3. So 2 pi minus 2 pi over 3 would be 4 pi over 3. And now we have our two roots on 0 to 2 pi. So now for part B, to get the general solution. So we're starting with the 2 pi over 3 and the 4 pi over 3, and we're looking at all the coterminal angles with those two angles. So we're adding multiples of 2 pi. And n has to be an integer. So you're adding 1 times 2 pi, or 2 times 2 pi, or 3 times 2 pi, or negative 1 times 2 pi, or negative 1 times negative 2 times 2 pi, and so on. So that completes this first example. Let's take a look at the next one. Now we notice that we've got two terms with sign x in it. So to solve this equation for all x, first we're going to have to put all the x terms together. So we've got 3 sine x equals 1. And if we divide both sides by 3, now we've got sine x isolated. Now, sometimes you may find the variable is listed as x and sometimes theta, but whenever you're looking for an answer to this variable and you've got an equation like sine of that variable equals some particular number, this is an angle. So if it is more comfortable for you, you can think about it as sine theta equals a third. And certainly that will help you to not get confused between x, y, r, and theta when you're drawing your little sketch of the angle and standard position here. In any case, we're looking at a situation where sine is positive, which means we're in quadrants 1 and 2. So if I sketch that out with a terminal arm in those two quadrants, and if I label sides that match this situation, remember that sine is y over r. So it's a 1 over 3. And 1 over 3 is also indicated in this quadrant. Now to get the remaining side, you can do 3 squared minus 1 squared and take the square root, and simplify that, you'll find it's 2 root 2. So now there's a first solution here in quadrant 1, and if I had to guess in degrees, it'd be somewhere around 20 degrees. In any case, it's not a special angle. And the second solution is here, and you'll notice that it's got the same reference angle, so we could subtract angle 1, x1, from 180 degrees if we're working in degrees, or subtract it from pi if we're working in radians. So what you need to do is punch in inverse sine of 1 over 3 in your calculator, again, because this is not just a special triangle situation where we've got ratios and angles memorized. So when you do inverse sine of 1 over 3, the calculator will give you 0.34 radians. Now, if you convert that to degrees, like I said, it would be somewhere maybe around 20 degrees. And of course, we're adding multiples of 2 pi because we want to get all the coterminal angles with that, because it says solve for all x, so not just on 0 to 2 pi. Now the second solution is pi minus the first, which is 2.80 radians, and in degrees it'd be somewhere around 160 degrees. And we want to add multiples of 2 pi to that to cover all the coterminal angles with it. Don't forget to mention every time you use that n is an integer. So that completes example number 2. Now we've got example number 3, which is a whole different animal. You'll notice that not only is it trigonometric, but it's also quadratic. So actually what we need to do with this initially is multiply these two numbers. We get negative 30. And we're looking for factors of negative 30 that add to 13. So that would be 15 and negative 2. And you can do decomposition if you like, if this is your method for factoring quadratics. If you've got another method like box method, you can use that. But if you use decomposition, then you'd take a look at the first two terms and you'd take out a greatest common factor, which would be 5 cosine x in this case. And then you take a look at the second half, the negative 2 cosine x minus 3. Take a look at what is the common factor. So that would be negative 1. And then you recognize that you've got two halves that both have 2 cosine x plus 3. So if you factor that out, and the other factor is 5 cosine x minus 1 equals 0. Okay, so this equation, the way that we solve it is we set each one of those factors equal to 0. So that means that cosine x would either have to be negative 3 over 2, or the other possibility is 1/5, which we'll get to in a minute. But first, let's look at, is it possible to have the cosine of an angle equal to negative 3 over 2? Well, no, that's impossible actually, because cosine of any angle is going to be between negative 1 and 1. So there are no roots on this part of the equation, or from these factors of the equation. Now, on the other side, it is possible to have cosine of an angle equal to 1/5. And so I'm going to sketch that out in standard position. I know that cosine is positive in this case, which means that I'm going to be in quadrants 1 and 4. And I'm going to draw terminal arms into each one of these quadrants, and I'm going to label the sides according to this situation. So again, if you're getting the x confused with theta and y and r, just think about it as being a theta. Okay, cosine of an angle is 1/5. And so we know that cosine is x over r, so it's 1 over 5. Of course, it could be 1 over 5 this way or 1 over 5 in quadrant 4. And just for completeness, if you're wondering what the y should be, what you can do is 5 squared minus 1 squared and take the square root. So that'd be 25 minus 1 is 24. Take the square root of 24, simplify it to simplest radical form, that would be 2 root 6. And so y could be positive 2 root 6 or negative 2 root 6. So in any case, this is the first solution, x1. And this is the second solution, x2. And notice they have the same reference angle. So you can get x2 by doing 2 pi minus x1. So I'm going to start with doing inverse cosine of 1/5, and that gives me x1 is 1.37 radians. And the other one is going to be 2 pi minus the first, which is 4.91 radians. So that solves example number 3. Let's take a look at the next one. So this one, again, is trigonometric, but it's also quadratic. So what we do with quadratics is we factor them. But of course, first of all, we have to talk about tangent. Tangent is a little bit of a different animal because there are restrictions on the domain of tangent. So we have to make sure if we get solutions to this equation, they don't turn out to be restricted values, because then we'd have to reject them. So here are the restrictions for a tangent. Pi over 2 is one of them, plus any multiples of 2 pi added on to that. Because if you take a look at that angle in standard position with an x of 0, a y of 1, and an r of 1, remember that tangent pi over 2, you would do y over x, 1 over 0. Well, this is undefined. Can't divide by 0, not even if you're Chuck Norris. The other situation is you've got an angle of 3 pi over 2, and if you add multiples of 2 pi to that, again, where n is an integer, then you're going to have an x of 0, a y of -1, and an r of 1. For instance, that's a point on the terminal arm of this angle. And if you try to evaluate the tangent of 3 pi over 2, you get y over x is -1 over 0. Well, again, this is undefined because can't divide by 0. You get something that's undefined. So these are the restrictions on x. It can't be any pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2. Basically, it simplifies to starting with pi over 2, adding multiples of pi. So notice that the first restriction is here at pi over 2, next one is at 3 pi over 2, and if we rotate around again, we get 5 pi over 2, and then 7 pi over 2, and so on. So starting at pi over 2 and adding multiples of pi, these are all the restricted values. Now, moving on to solving the trigonometric equation, we factor it first. So either tangent of x is 0 or tangent of x is 1. So for tangent x equals 0, you can see that an angle of 0 will work because the tangent of 0 over 1 will give you 0, so that works. And the other situation is pi. Notice that when you do the tangent of pi, you get 0 over -1, which is also 0. So it's 0 plus n times 2 pi or pi plus n times 2 pi. And again, we're adding multiples of 2 pi because that gives you all the coterminal angles with the original two solutions. So now if we take a look at where is tangent equal to 1, well, one of the solutions is pi over 4, because if you do tangent of pi over 4, you would get 1 over 1, which is 1. And the other possibility is 5 pi over 4, because if you do tangent of 5 pi over 4, you get -1 over -1 is also 1. I'm not available. So this angle is either pi over 4 or 5 pi over 4 plus multiples of 2 pi, where n is an integer. And now if we take these two situations and we simplify them a little bit, then the first one is 0 plus n pi, which is just n pi, because you'll notice that this one is 0, 2 pi, 4 pi, 6 pi. This one is 1, 3 pi, 5 pi, 7 pi. And so basically you have 0 plus 1 pi, 2 pi, 3 pi. So all of the multiples of pi are our solutions. And so the same thing happens with situation B. It simplifies to pi over 4 plus n times pi. And again, n is an integer. So final situation here, we're looking for the general solution of this. So if we factor it first, we're looking for factors of -2 that add to -1. So they are -2 and +1. We can do decomposition. Then we can look at the first two terms and take out the greatest common factor. Take a look at the next two terms and take out the greatest common factor. And so here it is in fully factored form. So next we're going to get cosine x equals -1/2 or cosine x equals 1. So just setting the first factor equal to 0 to cosine x plus 1 equals 0. Solve that for cosine x. You get cosine x equals -1/2. Or the other possibility is cosine x minus 1 equals 0, which means that cosine x would have to be equal to 1. All right, so we've already solved this first one, cosine x equals -1/2 in a previous example. So I'll just refer you back to example number 1 in case you've forgotten where that came from. And there's a more detailed solution there. So for the other part, where is cosine equal to 1? Well, that happens when the angle is 0. So you'll notice that when the angle is 0, here is the terminal arm. It's on the positive x-axis. I've picked a point on the terminal arm of the angle in the standard position. I've got an x-coordinate of 1, a y-coordinate of 0, and r is equal to 1. And cosine is x over r. So 1 over 1 gives us 1. And so this is the only angle on 0 to 2 pi that gives us a cosine of 1. So I start with 0, and then I add multiples of 2 pi to get all the coterminal angles to it that are part of the solution. And I'm going to specify that n is an integer. Now, most people would stop here. And this is totally fine. It's acceptable. It's correct. It's complete. But there's a special case scenario for this particular example, which is if you take those solutions and plot them all on the number line, you're going to realize there is a further simplification that can be done. So I wouldn't deduct if people miss this part, but I'm going to show it to you anyways, because sometimes, you're checking answers in the back of the book and they're really, really simplified and you're wondering why. So here's that explanation. So again, together on the number line, this is what it looks like. So we've got 0 and 2 pi and 4 pi and 6 pi. That's part of it. We also have 2 pi over 3 plus 2 pi plus 2 pi plus 2 pi. And then we've also got 4 pi over 3 plus 2 pi plus 2 pi plus 2 pi. And what you realize is that when you put them all together on the same number line, this whole thing together, it forms a single arithmetic sequence. And because you can simplify it into one arithmetic sequence, you can start at the smallest one x equals 0 and add multiples of 2 pi over 3. Because you can just go 0 plus 2 pi over 3 plus another 2 pi over 3 plus another 2 pi over 3 to get to all of the other solutions of this equation. Again, if you're giving your answer in terms of n, you should specify that n is an integer. But that's it. So thanks for watching this video lesson and have a great day.